Hello everyone. In this video, we present our work, Robustly Constrained Dynamic Games via System-Level Synthesis. We define robustly constraint-satisfying Nash equilibrium leveraging system-level synthesis and propose an efficient algorithm based on iterative best response to find the equilibrium. In the experiments, we will show that the feedback controller built with outputs of the algorithm ensures robust constraint satisfaction in multi-agent teams in both simulation and real-world deployment despite uncertain dynamics. In simulation experiments, we plot colored circles as agent volumes for AL games and as reachable sets for our method. We also plot two rollouts with identical disturbance sequences for each method along with nominal trajectories. In the narrow corridor experiment, we compare AL games with our method. It turns out that the open-loop controller generated by AL games causes collisions 91.8% of the time across 500 rollouts, while the feedback controller generated by our method never leads to collision. In the scaling experiment, we show that our method can scale to 24 agents, where collision avoidance constraints are robustly satisfied. We visualize the 8-agent case and show at the intersection, every agent stays in their reachable sets. Here is the visualization of the 24-agent case, with similar settings as the 8-agent case. In the state-dependent disturbance experiment, we compare AL games with our method. The result demonstrates the advantage of integrating trajectory planning to controller synthesis in our method, which enables agents to avoid the intersection with high disturbance and thus never violates collision avoidance constraint. However, AL games either causes collisions or deviates from the goals in the rollouts. In the hardware heterogeneous team experiment, we set 2 teams each with 1 quadcopter and 2 unicycles. Besides collision avoidance constraints, in each team, the middle unicycle needs to follow the quadcopter, and the unicycle at the end of the team follows the middle unicycle with proximity and line-of-sight constraints. In addition, only quadcopters are informed of the goal positions. From the top view, we can see that the leaders robustly stay in the cones representing proximity and line-of-sight constraints of followers, despite dynamics uncertainty. In the simulation heterogeneous team experiment, we have similar settings except for the dynamics of agents. Specifically, we use a 12D quadcopter model to show that our method can deal with high-dimensional state spaces.